Sea monsters are a staple feature of fantasy worlds, but those of you well versed in paleontology are probably well aware that many such creatures have existed throughout Earth's history. In ecological terms, a sea monster would be best described as one filling the macropredatory niche. This means it is among the largest creatures in the ocean, is at the top of the trophic ladder, and can kill and consume any other animal in the ocean. In today's video, we'll explore what kind of animals occupy this niche throughout the Phanerozoic. Going back to the Cambrian explosion, we find Anomalocaris, which has been described in BBC's Walking with Monsters as Earth's first superpredator. This species was first discovered from the Burgess Shale Formation, dated to around 500 million years ago. A well-known funny fact about it is that its fossils were discovered piecemeal and misidentified. Its feeding appendages were thought to be some kind of shrimp, its mouth was thought to belong to a jellyfish, and its body was thought to be one of a sponge. It wasn't until a complete specimen was found that paleontologists realized these separate species were all one of the same. In the Burgess Shale, trilobites would have been a readily available food supply, and likely were a staple of the Anomalocaris' diet. The Cambrian is often described as the age of the arthropods, with crown group arthropods, many of whom have an uncertain affinity within the arthropod clade, and to a lesser extent stem group arthropods, comprising the bulk of the animals roaming around the shallow seas at the time. Anomalocaris was part of a group of stem group arthropods known as the radiodonts. Another stem group arthropod was known as Opibenia. This species also had lateral flaps for locomotion, but instead of dual mouth parts, it had a trunk with a claw at the end. This species was also a predator, but at 7 centimeters in length, it was likely preyed upon by Anomalocaris, which could grow up to a meter long. So, we have the emergence of the whole "there's always a bigger fish" trope. In the older Maotianshan shales, which date to 530 million years ago, we find a close relative known as Innovatiocaris, which was originally assigned to Anomalocaris, but was later placed in its own genus. Its discovery shows that the Anomalocarids nabbed the macropredatory niche as soon as it opened in the Cambrian explosion. While Anomalocaris was a sea monster in that it acted as the top predator of the Cambrian period, such a creature would not have been a threat to a human if one could go back in time. But, if we fast forward about 50 million years, we can find some creatures that you probably wouldn't want to be in the water with. The Cambrian was followed by the Ordovician, which saw the rise of some of the most iconic marine fauna of the Paleozoic, such as the jawless fish, nautiloids, and sea scorpions. Now, sea scorpions weren't actually scorpions, but a distantly related group of arthropods known as the Eurypterids. Arguably, the fiercest one of these dated from the Ordovician was Megalograptus, which was armed with long spines on its forelimbs. It would have used these to impale prey such as trilobites and early jawless fish, our distant ancestors. With a body length of 80 centimeters, this creature could certainly inflict pretty serious injuries on a person, but Megalograptus wasn't even the fiercest predator in the Ordovician seas. That distinction goes to Cambrian, a nautiloid with a 5.7 meter long shell, and this animal was certainly capable of killing a person. It likely had a varied diet, which included trilobites, other nautiloids, and Eurypterids, including Megalograptus, the whole "there's always a bigger fish" trope/theme. It should be noted that there likely was some niche partitioning between nautiloids and Eurypterids, with nautiloids hunting in the water column, while Eurypterids hunted on the seabed, although many Eurypterids, including Megalograptus, could swim. The Ordovician ended with the first of the 5 great mass extinctions in Earth's history. Both the nautiloids and Eurypterids survived, but the extinction caused a role reversal between them. In the subsequent Silurian period, Eurypterids became the top predators, the largest of these being Pterygotus, which grew up to 1.7 meters in length. Like true scorpions, Eurypterids were chelicerates, a group defined by their fang-like mouthparts or chelicerae. These arthropods also have two forward-facing appendages or pedipalps and 8 limbs. However, while the scorpion's pincers are its pedipalps, in Pterygotus, the pincers are the chelicerae. The pedipalps of Pterygotus acted like a front pair of limbs, and the last pair of limbs acted as swimming paddles. Trilobite diversity and abundance took a hard hit at the end Ordovician extinction, and many of the niches they filled were occupied by jawless fish who underwent an adaptive radiation in the early Silurian. Furthermore, many of these fish occupy nectonic or free-swimming niches, making the water column much more functionally diverse than it ever was before. Such animals would have been a staple of Pterygotus's diet. Apart from Eurypterids, actual scorpions who lived in the water, or true sea scorpions, prowled the seabed. One of these was Brontoscorpio, which would have grown to a meter long. Exactly how this species fits into the scorpion family tree is still debated, but most likely it was a stem group scorpion, or one closely related to, but not descended from the last common ancestor of all living scorpions. All we've recovered from it is a pedipalp, so it's hard to say what it looked like, but many early scorpions had quad pincers, with their pedipalps forming the larger pair like modern scorpions, while the chelicerae formed a smaller pair like Pterygotus. That in and of itself might feel terrifying enough, but remember, the smaller pair would have been comparable in size to the pincers of modern scorpions. The Cambrian, Ordovician, and Silurian constitute the early Paleozoic era, and the subsequent Devonian period marked the start of the late Paleozoic. In the early part of the Devonian, Eurypterids continued to occupy the quote-unquote super-predator niche. They continued to grow in size, with one species known as Jacalopterus rhenaniae growing to a body length of 2.5 meters and a mass of over 380 kilos. This animal may very well have been the largest arthropod of all time, with another Eurypterid, which lived later, known as Hibbertopterus, possibly having been larger. Although Hibbertopterus was a sediment-foraging detritivore, while Jacalopterus was certainly a predator. Jacalopterus was similar in morphology to Pterygotus, with swimming paddles and cheliceral pincers, and likely lived a similar lifestyle. However, Jacalopterus was recovered from ancient estuarine sediments, so we're not sure if it was a sea monster or a river monster. Like Pterygotus, fish was likely a staple of Jacalopterus' diet, and while jawless fish were still common in the early Devonian, jawed fish underwent an adaptive radiation around this time. One group of these, known as the placoderms, with their iconic bony-plated heads, rapidly occupied predatory niches, and these outcompeted the large predatory Eurypterids in the early to mid-Devonian. By the mid-Devonian, large placoderms occupied the niche of top predator in most of the world's oceans. The largest of these is perhaps the most iconic Paleozoic sea predator, Dunkleosteus. Just looking at the skull of this creature, you can tell it was a formidable predator in life. Instead of teeth, which would have penetrated the flesh of its prey, it had shearing bony plates on the sides of its mouth, which could cut small prey in half. So far, we've only found the head region of Dunkleosteus, and from this, paleontologists have attempted to estimate its size. Historic estimates have put it around 9 meters in length, but these are based on head size to body size ratios of sharks. Recent estimates based on the complete fossils of other placoderms gave an estimate of about 5 meters. Not the monster you once thought it was, but still pretty ferocious nonetheless. Another aspect of historic reconstructions of Dunkleosteus may also be inaccurate. Those of you who are into paleontology know that a hot topic for dinosaurs is shrink wrapping. Many old reconstructions, and by old I mean 90s and 2000s, show the skin wrapped tightly around the skull to the point where you can see processes and holes in the skull. But if we look at modern reptiles, we can't see such features because there's so much soft tissue over the skull, and it's likely that dinosaurs had comparable amounts of soft tissue. When we look at reconstructions of Dunkleosteus, there is no or minimal soft tissue over the bony plates, but pretty much all animals with bony plates have soft tissue over them, and it's likely that Dunkleosteus had the same. This also means the fearsome mouth plates were also covered up by lips. Although, before you get too bummed out about this, some fish like the Goliath tigerfish have teeth exposed even when their mouth is closed, so the dermal plates of Dunkleosteus might have been visible even when its mouth was closed. The Devonian is often referred to as the age of fishes, and Dunkleosteus would have shared the sea with many other fish such as the lobe-finned Eusthenopteron, a distant relative of the fish who would crawl out of the water to become the first tetrapods, and the early cartilaginous fish Gladosilach. Such animals, along with smaller placoderms, would have been regularly taken as prey by Dunkleosteus. Another placoderm known as Titanichthys grew to a similar size in the Devonian, but whereas Dunkleosteus was a macropredator, Titanichthys was a filter feeder, sieving out plankton from the water. So, Dunkleosteus could have also taken Titanichthys as prey, i.e., it may have also attacked animals similar to its own size. While placoderms flourished in the Devonian, two mass extinctions, one in the late Devonian and the other at the end of the Devonian, wiped them out. The later Carboniferous period saw the extension of the cartilaginous fish, i.e., ancient relatives of sharks, skates, rays, and chimeras. These diversified to fill many of the ecological niches bony fish do now, while some occupy the apex predator niche, in a manner somewhat similar to modern sharks. One group of cartilaginous fish, the Stenacanthiforms, seem to have capitalized on this niche. These are characterized by large spines on their dorsal fins, and one species known as Glycmonus occidentalis grew up to 6 meters long, making it comparable to a modern great white. The cartilaginous fish family tree splits into two main groups, the Elasmobranchii and the Holocephali. The former include sharks, skates, and rays, while the latter only has one surviving member, the deep-sea chimeras. While rare in the modern oceans, the Holocephali reach comparable levels of diversity to contemporary elasmobranchs in the Carboniferous. One group, known as the Eugeniodontids, also occupied apex predator niches, and they did so with some pretty unique dentition. The ancestor of this group had evolved a single row of teeth at the front of their upper and lower jaws, which would have acted like a pair of serrated scissors. One of the Eugeniodontids with this tooth arrangement was Adestus, who could have grown to 6.7 meters in length, which would have made it the largest predator to exist up until that point. But it wasn't long before this record was nabbed by someone else. In one group of Eugeniodontids, known as the Helicoprionids, the lower row of teeth evolved into a whorl. These are colloquially referred to as the buzzsaw sharks, and one genus, known as Campylcoprion, which lived near the end of the Carboniferous, grew to 9 meters in length. During the subsequent Permian period, the top predator niche continued to be occupied by chondrichthyans. On the elasmobranch side, we have Cahobvinator, a Stenacanthiform, which grew to 5 to 6 meters in length, and on the holocephalian side, we have Helicoprion, which grew to a whopping 7.6 meters in length. As its name suggests, Helicoprion was a whorl tooth. One might expect that there was intense competition between large elasmobranch and holocephalian apex predators in the Carboniferous and Permian, but I don't think this was the case. Eugeniocodontids had rather thin and gracile teeth, while Stenacanthiforms had deeply rooted conical teeth. This would suggest that the Eugeniocontids mostly preyed on soft-bodied animals, like clovioid cephalopods, while Stenacanthiforms preyed on bony animals such as fish. Basically, they avoided competition via niche partitioning. The end of the Permian saw the greatest mass extinction in Earth's history, and it was particularly bad in the oceans, with 95% of all marine species going extinct. The exact cause is debated, but it seems to have been linked to the Siberian traps, a large basaltic province which erupted 252 million years ago. The carbon dioxide released by the eruption spiked the global temperature by about 5 degrees. This sudden shift led to severe storms, which washed organic matter into the ocean. This in turn led to anoxic, followed by sulfitic conditions, as microorganisms used up the oxygen in the water column and respired sulfate instead, producing hydrogen sulfide. Most marine organisms were either suffocated or poisoned. While chondrichthyans as a group survived, stendacantiforms went extinct, along with virtually all eugeniodontids. And the eugeniodontids would go extinct about 5 million years later. This mass extinction not only ended the Permian, but ended the late Paleozoic era, giving rise to the Mesozoic, or the Age of the Dinosaurs. In the desolate oceans of the early Triassic, some reptiles, whose ancestors crawled out of the water 120 million years earlier, returned to the sea. These were the iconic ichthyosaurs, with the oldest fully aquatic one, Gripia, having lived 248 million years ago, only 4 million years after the end Permian extinction. Ichthyosaurs continued to rapidly evolve and diversify in the early Triassic, with one species known as Symbispondylus youngorum growing to 17 meters in length. That would make it comparable in size to the modern gray whale, the smallest of the great whales, and it lived only 4 million years after ichthyosaurs became fully aquatic. At the same time Symbispondylus lived, we find the Ladoarchon saurophagus, and those of you well versed in scientific names can probably tell its name means lizard eater. This is because it had a robust skull and deeply rooted teeth, and this would have made it well suited for taking large prey such as other marine reptiles. I like to call this species the first modern sea monster. One of the key differences between the seas of the early and late Paleozoic and those of the Mesozoic and Cenozoic is that in the latter, many of the ecologically dominant niches were dominated by secondarily aquatic amniotes, i.e. marine reptiles and marine mammals. As such, when we think of a sea monster in this context, it would be one who preyed on secondarily aquatic amniotes, making it an apex predator, and the Ladoarchon appears to have been the first animal to have specialized in taking such prey. The Ladoarchon grew to 8 meters in length, making it more than capable of taking a human time traveler who went for a swim in the early Triassic seas. Smaller ichthyosaurs, such as the meter-long Mixosaurus and the 2.5-meter-long Utatsusaurus, would have been regularly taken as prey by the Ladoarchon. Around this time, other reptiles were exploring becoming secondarily aquatic, including the iconic long-necked Tanystropheus, and the Ladoarchon likely took them as prey when it had the chance, although these could escape to the shore for safety. While ichthyosaurs are known for their fish-like shapes, the Triassic forms had morphological features characteristic of animals who more recently returned to the sea, such as a more flexible neck, distinct bodies and tails, and only the lower half of the tail fluke, although some of these early forms did have dorsal fins. Although ichthyosaurs evolved an aquatic lifestyle very quickly, what's truly amazing is that they were able to do so and diversify in the early Triassic, when the rest of the marine fauna didn't globally recover from the end Permian extinction until the mid-Triassic. With the marine radiation, we see early relatives of the iconic plesiosaurs evolve increasingly aquatic lifestyles, such as Nothosaurus. When we think of Mesozoic sea monsters, many of us will probably imagine either a giant pliosaur or a mosasaur, while ichthyosaurs will just be swimming in the background. However, in the past decade, a series of discoveries have shown that the ichthyosaurs went from strength to strength in the reinvigorated Triassic seas, reaching sizes and ferocities which surpassed any later marine reptiles. For a long time, it was thought that Chonisaurus was the largest ichthyosaur, which grew up to 15 meters in length and weighed 33 tons, making it comparable to the humpback whale. Then, in 2004, a specimen of another species, Shastasaurus sicaniensis, was found, and this would have grown to 21 meters in length and weighed in at over 70 tons. Both Chonisaurus and Shastasaurus were shastasaurids, and these had a trend to evolve gigantism in the late Triassic. If ichthyosaurs could be described as the dolphins of the Mesozoic, The Shastasaurids were the whales of the Triassic. With its long, slender snout, it was initially thought that Shonisaurus would have been a gentle giant, taking prey that would have weighed less than 4 kilos. However, a recent analysis of its teeth showed that they were deeply rooted, meaning it could have taken larger prey than previously thought, including 1 to 2 meter long coelacanths, and possibly even small ichthyosaurs such as Hudson-Alpedia. Needless to say, I wouldn't want to be in the water with a live one. Then, in 2018, a bone unearthed long ago was identified as part of a syringular of a Shastasaurid. Based on the size of the bone fragment, it's estimated that the animal who possessed it could have grown to 25 meters in length and weighed in at 120 tons, making it comparable to the average blue whale. This animal is recently named Ichthyotitan, and 2 other syringulars have been found at nearby sites in the United Kingdom. The syringular is quite long, suggesting a skull shape similar to Shonisaurus, and it had very strong neck muscle attachments, which also suggests that, like Shonisaurus, it could take larger prey than its gracile jaws would suggest, and while not capable of killing other large ichthyosaurs, was not averse to taking human-sized prey. Another part of a syringular was found at the Aust Cliff, which is larger than the corresponding part of the previously found syringulars. The remains are too fragmentary to know for sure if they belong to an Ichthyotitan, but if they are, the specimen would have grown to over 30 meters in length and weighed 175 tons in life. If the Aust colossus is indeed a large Ichthyotitan, that would put their average weight at 134 tons, making it the largest animal ever. Now, you might argue that the blue whale can grow up to 210 metric tons, but that's the largest ever recorded out of thousands of specimens documented, while we only have found 3 to 4 Ichthyotitans, so the odds we found the largest are next to 0. But, in defense of the blue whale, if Ichthyotitan had an average weight of 120 tons, while the odds that we find the remains of a record-holding 210-ton individual are statistically non-existent, say 2% of Ichthyotitans in blue whales grew to 175 tons or larger. If you found 4 Ichthyotitan specimens, the odds you'd find one of these supersized individuals would be about 8%. This isn't something to bet on, but it's not something to be written off as a statistical fluke if it happens either. So, the blue whale could still be at least tied for the title of the largest animal ever. And of course, there's the usual caveat that with fragmentary remains, it's hard to get good size estimates. But enough about supersized sea reptiles that may or may not have taken human-sized prey. This video is supposed to be about animals who could turn any other creatures in the sea into mincemeat. And for that we have another late Triassic Shastasaurid, Himalayasaurus tibetensis. This species grew up to 15 meters in length, and with a broad, stout skull and large, deeply rooted teeth, it was well suited to prey on other large marine reptiles. At 40 tons, it was comparable in size to the largest pliosaurs, but another 2018 find showed its relatives could grow even larger. A tooth found in the Swiss Alps was similar to those of Himalayasaurus, but were larger. Scaling up based on the tooth size, it's estimated that the ichthyosaur who possessed it, known for now as the Swiss tyrant, could grow to 18 meters in length and weigh 60 tons, making it the largest macropredator of the Mesozoic seas, and by implication, the ultimate sea monster of the age of the dinosaurs. Sorry if that sounded a bit too bro-paleontology. Pretty much anything would have been on the menu for this animal. Sharks, other ichthyosaurs, early plesiosaurs, hell, it may have even gone after Ichthyotitan. Speaking of which, while it has been proposed that the Aust colossus specimen was a large Ichthyotitan, maybe it came from a smaller ichthyosaur. Because they have to be able to stand the stress of struggling prey, the jaws of macrophagous predators have to be posteriorly-anteriorly compressed. This would mean that the circumference of the anterior portion of the syringular would be larger relative to the size of the skull, and by implication, the rest of the animal. Basically, if the Aust specimen came from a macrophagous ichthyosaur, the overall size estimates would be smaller, but still quite large. So, perhaps the Swiss tyrant and Aust colossus are one of the same species. The end of the Triassic saw the fourth great mass extinction in Earth's history, with this one being linked to rapid climate fluctuations and ocean acidification/anoxia. While the ichthyosaurs as a group survived, the giant shastosaurids went extinct. One group who evolved in the late Triassic, known as the Neoichthyosaurines, survived the extinction and diversified in the early Jurassic. These ichthyosaurs had the iconic fish-like shape that we see in many paleo-reconstructions. While the Triassic was the heyday of the ichthyosaurs, some like Temnodontosaurus were able to occupy the apex predator niche in the early Jurassic seas once they recovered from the end Triassic extinction. Even though it had a fairly long snout, Temnodontosaurus had a robust skull and thick sharp teeth and would have preyed on other ichthyosaurs and the long-necked plesiosaurs. Temnodontosaurus persisted from 200 to 175 million years ago, at which point the large ichthyosaurs faced increased competition from other marine reptiles, although smaller ones like Ichthyosaurus remain common. One group of newcomers was the Thalattosaucians, stem group crocodiles who evolved an increasingly marine lifestyle over the course of the Jurassic. The largest of these from the Jurassic was Macropredator, which at the time grew to 7.15 meters in length, making it comparable to the modern saltwater crocodile. With a similarly built skull, it also would have lived a similar lifestyle, both hunting in the ocean and ambushing prey by the shore. Macropredator and its relatives had legs similar to modern crocodilians, and would have come out of the water regularly. However, one group of Thalattosaucians, known as the Metriorhynchids, evolved more adaptations to a life in the sea, such as paddle-like limbs and a tail fluke. The Metriorhynchids split into two main groups, the Metriorhynchinae and Geosaurinae. The Metriorhynchinae developed a long, slender snout with gracile sharp teeth, which were ideal for snapping up fish and squid. Meanwhile, the Geosaurinae had short, broad snouts with larger, thick teeth, which would have been well suited for dismembering larger prey. The largest of these was Plesiosuchus, at 6.8 meters in length, making it comparable to Macromosaurus, but the most well suited for hunting prey of comparable size to itself was the 4.5 meter long Dacosaurus with a deep skull. But, as fearsome as these creatures were, they would have been fodder for the largest predators to haunt the late Jurassic seas. These were the pliosaurs, plesiosaurs with short necks and large crocodile-like heads. Those of you who grew up in the 90s and watched Walking with Dinosaurs probably remember the infamous Gigaplorodon. Basically, they portrayed the pliosaur Liopleurodon as being 25 meters in length and weighing at 150 tons, eating anything that swam. Looking at the skull of this animal, it's pretty clear that it was capable of taking prey of comparable size to itself, but the actual size was between 4 and 8 meters in length and weighing in at 4 tons. So, where did the Gigaplorodon come from? Well, very fragmentary remains of a large pliosaur were recovered in England. Some paleontologists believe these remains to have come from Liopleurodon and gave an estimated total length of 20 meters, but this doesn't seem to have been the case. However, other lines of evidence indicated that a very large pliosaur was inhabiting the oceans at the time, such as bite marks on the bones of long-necked plesiosaurs. In 2007, a skull in Svalbard belonging to a giant pliosaur was dug up. This animal was originally known as Predator X and later scientifically labeled Pliosaurus funki. The original skull was 2 meters in length, with one found later measuring 2.5 meters, and the total length of the animal is estimated to have been between 10 and 12 meters, and the weight between 36 and 45 tons. This would make Pliosaurus funki the largest plesiosaur, and while it certainly hunted other marine reptiles, such as the Thalattosaucians, other plesiosaurs, and ichthyosaurs, it likely also hunted prey even larger than itself. The largest creature in the late Jurassic oceans wasn't a marine reptile, but a large bony fish known as Leedsichthys. This animal was a filter feeder, living a similar lifestyle to the modern whale shark, and it grew to 16.5 meters in length. This gentle giant could have been a major food source for Pliosaurus fungi. 145 million years ago, a minor mass extinction ended the Jurassic period and began the Cretaceous. This delivered a harsh blow to the plesiosaurs, but devastated the ichthyosaurs, with only a few species persisting into the Cretaceous. Throughout much of the early and mid-Cretaceous, pliosaurs remained the apex predators of the oceans, with Kronosaurus, the largest species known from this time, growing up to 11 meters in length. The aforementioned Macropredator also survived the end Jurassic extinction and grew to even larger sizes in the early Cretaceous, with fragmentary remains recovered in Colombia, indicating that one species known as Macropredator rex could grow to 9.6 meters in length. But in the late Cretaceous, they would have some serious competition. 95 million years ago, another group of reptiles, the mosasaurs, returned to the sea, and around this time, the last of the ichthyosaurs died out. While there is an ongoing debate as to how the ichthyosaurs and plesiosaurs are related to the other major groups of reptiles, it was clear from the start where the mosasaurs fit into the reptile family tree. They were lizards. More specifically, they were related to snakes. Yes, snakes were lizards. We found a close amphibious relative to the mosasaurs known as Dallosaurus from 92 million years ago. They likely evolved in response to the rising sea levels in the mid to late Cretaceous. The largest of these, Mosasaurus, is estimated to have grown to 17 meters in length, while the largest complete skeleton belonged to an animal known as Tylosaurus, which grew to 15 meters. Both Mosasaurus and Tylosaurus had skulls well adapted to taking large prey, and they even had a third row of teeth in their upper jaw. While the mosasaurs were the undisputed kings of the late Cretaceous seas, there were some other very fearsome animals haunting the waters. If you thought big scary fish were a thing of the late Paleozoic, there was the shark Cretoxyrhina, which grew to 8 meters in length and weighed in at 5 tons, twice the size of a large great white. There was also the fierce-looking Xiphactinus, which grew to 6 meters in length. To get even more retro, if you thought invertebrate sea monsters were a thing of the early Paleozoic, there was Enchotuithus, a squid-like octopus relative with a hood that could grow to 2 meters in length and an overall length of 3 meters. On top of that, there was the giant ammonite Parapuzosia, with a shell that could grow to at least 1.8 meters in diameter, and fragmentary remains indicated that some specimens could have a shell that grew between 2.5 and 3.5 meters in diameter. There were also other animals like Archelon, a giant sea turtle which grew to 4.5 meters in length and weighed up to 3.5 tons, and Hesperornis, a penguin-like stem group seabird which grew to 2 meters in length. While not sea monsters, these animals were still fascinating in their own right. On a previous video, someone asked how mosasaurs were able to become secondarily aquatic despite the presence of plesiosaurs, because intuition would state that they would competitively exclude them. If I were to guess, it would come down to how they move. Plesiosaurs swim via movements of their flippers, while mosasaurs did so via undulations of their spine. This is a recurring theme we see in the Mesozoic and the Cenozoic. In the Triassic, plesiosaurs were able to become secondarily aquatic despite the presence of ichthyosaurs in the oceans, and like the mosasaurs, ichthyosaurs swam by undulating their spine. So, kind of like the converse of what happened with the mosasaurs and plesiosaurs. Later in the Cenozoic, pinnipeds were able to evolve a secondarily aquatic lifestyle despite the presence of cetaceans, and pinnipeds use their flippers to swim while cetaceans undulate their spine. Although, unlike the marine reptiles, they do so in a vertical versus horizontal motion. These different methods of locomotion convey a different series of advantages. For example, swimming using flippers gives greater maneuverability, while doing so via undulations gives greater speed. With different methods of locomotion comes different feeding strategies. With different feeding strategies comes different prey preferences, and with different prey preferences comes reduced competition. So, it may be that employing either method of swimming will result in occupying separate sets of niches. This might also explain why mosasaurs look very similar to early ichthyosaurs, And who knows, maybe had the end Cretaceous extinction not happened, Mosasaurus would have evolved a fish-like shape similar to that of the Neoichthyosaurians. We could call this spec-evoclade Euichthyosaurs, meaning true fish lizards, Eu meaning true because Mosasaurs were actually lizards. But alas, the end Cretaceous extinction happened 66 million years ago, and on top of the non-avian dinosaurs, it wiped out all the marine reptiles except for the turtles. At this point, the Mesozoic gave way to the current era, the Cenozoic. The Cenozoic is divided into the Paleogene and Neogene periods, and the first epoch of the Paleogene is the Paleocene. With the large predatory sea reptiles now extinct, sharks filled the role of apex predator. One genus, Cretalamna, had its origins in the Cretaceous and survived the mass extinction. Growing to between 3 and 4.5 meters in length, they would have dominated the Paleocene oceans, but this was just a foreshadowing of what their descendants would become. However, as the Paleocene ended and the Eocene began 56 million years ago, they would start to have some serious competition. In the early Eocene, the ancestors of whales began to evolve an increasingly aquatic lifestyle. One of these amphibious proto-whales was Ambulocetus, which means walking whale. It grew to 3 meters in length and looked for all intents and purposes like a mammalian crocodile. About 10 million years later, the basilosaurids appear in the fossil record, and these were the first fully aquatic cetaceans. The first member of this group to be described is Basilosaurus, whose name means king lizard. This is because upon its discovery, it was originally thought to be a mosasaur due to its slender serpentine build. Speaking of serpentine things, in the Eocene, you had Palaeophis colocaeus, a 13-meter-long sea snake that could have weighed 2.5 tons. Yeah, big scary marine reptiles weren't just a thing of the Mesozoic. While fully aquatic, basilosaurids retained a few features from their terrestrial ancestors absent in modern whales, such as unfused neck vertebrae, a pivoting elbow joint, distinct incisors and molars, and some had vestigial back limbs. Basilosaurus grew up to 20 meters in length and weighed between 12 and 15 tons. An analysis of its gut contents showed it ate a variety of prey such as sharks, nautiloids, and a dolphin-sized early whale known as Durodon. Apart from whales, sirenians, dugongs, and manatees began to return to the sea in the Eocene, and the ones in the late Eocene were still amphibious like Peristomus, and Basilosaurus probably would have nabbed one if it caught them swimming in deep nearshore water. Speaking of manatees, you may have heard that last year they found a giant relative of Basilosaurus known as Pericetus, which has been described as a whale manatee. Its discovery made headlines when it was claimed that it was larger than a blue whale at between 85 and 340 tons, but these estimates relied on very questionable scaling methods. Later estimates gave a mass of around 60 tons, which would make it the largest animal of the Eocene, but not the largest that ever lived. This is also why we should take claims of the aforementioned Ichthyotitan being the largest animal ever with a pretty large pinch of salt. As for being a whale version of a manatee, well, both Pericetus and Sirenians had very thick bones, which weighed them down and made feeding on the seabed easier. However, while Sirenians eat algae and marine plants, Pericetus likely foraged for shellfish, so it was more like a supersized walrus. The Eocene ended with a mass extinction, which was likely linked to the glaciation of Antarctica 34 million years ago. The stem group whales such as Basilosaurus were wiped out in the extinction, but the crown group whales, or the descendants of the last common ancestor of all living whales, diversified in the Oligocene. Among these were the progenitor of the baleen whales such as Mammalodon, and many early toothed whales. One of these, known as Ankylorhiza, grew up to 5 meters in length. It had a fairly long rostrum compared to modern dolphins, but it also had many larger, deeply rooted teeth, and an unusually powerful bite force for a cetacean. Just looking at the skull and dentition of this animal, you could tell it was capable of killing large prey. This would be mostly constituted of large fish, but Ankylorhiza could have taken small amphibious animals who ventured too far into the water. But, as fearsome as this creature was, it may not have been the top predator of the oceans. It's around this time that the descendants of the aforementioned Cretalamina start to become much larger. The genus Otodus, or the megatoothed sharks, first evolved in the Eocene with Otodus okolovi, which grew to 6 meters in length, making it comparable to the largest great whites. In the Oligocene, they continued to grow in size, with Otodus augustedens growing to between 11 and 12 meters in length. At this size, this animal could have hunted anything that swam in the seas, including Ankylorygia. Ah, the whole there's always a bigger fish trope. Around 23 million years ago, at the start of the Miocene, we first find the remains of the largest member of the genus Otodus, and, arguably, the most famous sea monster of all time, Otodus megalodon. It was initially thought that megalodon was a close relative of the modern great white, and thus placed in the same genus known as Chaetodon. However, this seems to have been a knee-jerk reaction. The great white is the largest predatory shark alive today, and megalodon is the largest predatory shark of all time, so placing them together only seemed natural to Victorian-era paleontologists. But if you look closely at the teeth, you can see that the great white and megalodon teeth don't look so similar. I mean, sure, there'll be some similarities because they specialized in taking mammalian prey, but detailed morphological analysis of the teeth indicated that the great white is more closely related to the mako shark, while megalodon is in a now extinct clade known as the otodontids. Based on these false assumptions, many have attempted to estimate megalodon's size by scaling up from the great white, with maximum length estimates between 14 and 18 meters, and maximum weight estimates between 50 and 100 tons. However, a disarticulated but complete vertebral column from megalodon found in Belgium was analyzed, and it indicated that the proportions of megalodon were more elongate than the great white, implying the upper length estimates and lower weight estimates were probably the correct ones. Throughout the Miocene, megalodon had a worldwide or cosmopolitan distribution, and while it could kill pretty much anything that swam, its preferred prey would have been cetatheres, small baleen whales that grew up to the size of minke whales. But not to be outdone, the mammals produced some pretty fearsome creatures in the Miocene seas, which could have given megalodon a run for its money. The most prominent of these was Livyton melvilli, a raptorial stem group sperm whale. This animal was originally identified from a 10 million year old skull found in Peru, and said skull was 3 meters long, 2 meters wide, and had 36 centimeter long teeth. For some perspective, those of megalodon were 18 centimeters long, and those of Livyton were the largest functional teeth of any vertebrate. Just by looking at the skull, you can tell that this was a fearsome animal in life, and paleontologists have also attempted to estimate its size. These estimates are based on the skull size to overall size ratio of some of its relatives, who we found complete fossils of. The shortest lengths are around 13.5 meters long, while the longest are a whopping 17.5 meters long, and maximum weight estimates are around 55 tons. Since the first skull was found in Peru, we've also found a tooth in Australia, indicating Livyton's distribution at least spanned across the southern Pacific Ocean. Like megalodon, cetatheres were likely a staple of Livyton's diet. Megalodon teeth have been found in the sediments the original Livyton skull was recovered from, indicating that these two species cohabited. How two supersized macrophagous predators could share the same habitat is a bit of a mystery, and challenges some long-standing assumptions we have made about niche partitioning. But the fact that they did cohabit does raise an obvious question. Who would win if these two creatures, arguably the two most powerful predators ever to prowl the oceans, crossed paths? Well, first of all, such clashes would be rare, since big predators usually make a mutual effort to stay away from each other due to the risk of an injury that would come with such an encounter. Second, with only fragmentary remains known from either combatant, there's too many unquantified variables to get an even remote idea of who would win in a direct confrontation. However, I will address some recurring problems that come up when people try to figure out who would win in a fight. First, many paleo reconstructions show Livyton preying on megalodon in a manner similar to how modern orcas prey on great white sharks. This is problematic for two reasons. First, orcas have an over 2-to-1 size advantage over modern great whites, while Leviathan and Megalodon were more comparable in size. Second, Leviathan isn't a giant orca, and, as we discussed earlier, Megalodon isn't a giant great white. But on the flip side, many who argue that Megalodon would win show Megalodon being quite a bit larger than Leviathan. This is a bit deceiving because they are using the largest Megalodon specimens we found remains from. Over the course of the past century, we found teeth from hundreds or even thousands of individual Megalodons, and even though we probably didn't find teeth from the largest Megalodon to ever live, some of the teeth recovered were certainly from the largest 1% of individuals. Meanwhile, we found a skull from a single Leviathan specimen, which those reconstructions were based off of. So, a lot of these side-by-side comparisons are showing the largest Megalodon individuals to what is in all likelihood an average-sized Leviathan. If you had a Leviathan superimposed next to an average-sized Megalodon, their sizes would be much more similar. While Leviathan was certainly the fiercest among them, Miocene sperm whales were a far cry from the gentle squid-eating suction feeder we have today. One of these was Zygophyseter, which grew to 7 meters long and, at first glance, would look something like a cross between a sperm whale and a bottlenose dolphin. But, if you look at its teeth, they were similar in shape to those of Leviathan, indicating that it was adept at taking large prey. This likely occasionally included other cetaceans such as the bizarre Odobenocetops, but also possibly the Lacnosus, a semi-aquatic ground sloth which would have grazed on aquatic plants and algae in the shallows off the Pacific coast of South America. Apart from sharks and cetaceans, other groups of marine animals in the Miocene became very ferocious predators, and while they got nowhere near as big as Megalodon or Leviathan, unlike them, you wouldn't have been safe from these on land. In the Oligocene, pinnipeds also evolved a secondarily aquatic lifestyle, and in the Miocene, they diversified into their modern varieties. Among these was Pontolis, a prehistoric walrus the size of an elephant seal that was as voracious as a leopard seal. This animal lived on what is now the Pacific coast of the U.S., and one likely prey item would have been the Desmostylians, a now extinct order of herbivorous marine mammals that were essentially marine hippos. On the Indian coast, there is Ramphosuchus, a relative of the gharial that grew up to 11 meters in length. Yes, giant crocodiles weren't just a thing of the age of the dinosaurs. While the Mesozoic may come to mind when we think of the age of prehistoric sea monsters, with so many large macrophagous carnivores, the Miocene seas were arguably the most thalassophobia-inducing in Earth's history. By the start of the Pliocene epoch 5.3 million years ago, many of these large predators had died out, but the most iconic of all, Megalodon, persisted. While the end of the Eocene saw Antarctica become glaciated, the start of the Pliocene saw sea ice first cover the Arctic. It's around this time that we see baleen whales go from the medium-sized forms seen in the Miocene to the giants we see today. In some of these giant whales, we find Megalodon teeth embedded in their remains, implying Megalodon took them as prey as it did their smaller ancestors. It was in the late Pliocene that Megalodon finally died out 3.6 million years ago. It's not certain why this happened, but the most compelling hypothesis is a drop in productivity linked to the joining of the Americas. This in turn led to a decrease in the food resources, which then led to increased competition, and this resulted in Megalodon being squeezed out by smaller predators. Now, there are some who would argue that Megalodon survived past 3.6 million years ago. One line of evidence for this is a tooth that was dated to 12,000 years ago. However, this tooth was dated via manganese oxide accumulation, which is notoriously inaccurate. An attempt was made to corroborate this date by carbon dating, but no organic carbon could be extracted to analyze, and if the tooth was that young, they should have been able to get organic carbon from it. Others would argue that Megalodon survives in the deep sea, and an argument in support of this is that a U.S. submarine supposedly tracked an enormous whale-sized animal in a trench near Puerto Rico that stayed underwater for hours. If this was actually a whale, it would have surfaced during this time. But the problem with the idea that Megalodon survives in the deep sea is that it was specialized in preying on whales, and being air breathers, they tend to stick close to the surface. I'm not sure how credible the aforementioned submarine story is, but if there is indeed a supersized animal living in the deep sea, it would be more likely to be something like a supersized sleeper shark versus a late surviving megalodon. With Megalodon gone, do we have any sea monsters now? Well, the apex predator of the modern oceans is the orca, but instead of using size or powerful jaws to take down the largest animals in the sea, they utilize teamwork. Orcas may seem quite different from other apex predators which inhabited the sea in the distant past, but can we be certain of that? I mean, orcas don't have any anatomical features that suggest that they are macrophagous predators, and when another civilization develops millions of years in the future, and their version of paleontologists dig up their bones, they'll probably think they just ate fish and squid like other dolphins. They would have no idea that orcas were apex predators until maybe they analyzed the nitrogen isotope composition of their bones and found out that they were unusually high on the trophic pyramid. And even then, many would likely doubt that they were hunting giant whales until they find evidence of behavior like an orca tooth embedded in a fin whale bone. It really makes you wonder if any seemingly mundane prehistoric marine animal might have adopted a similar lifestyle and dominated the seas. And who knows, maybe we'll find out that someone else was really a quote-unquote sea monster when we analyze the nitrogen isotope composition of their remains. It really makes you wonder what's truly hidden in our past.